This is week number 5. And the main thing we're going to do today is sheaf cohomology. But using the modules that we did. So it's all extremely explicit and nice. So there's no, you don't have to know anything about sheaves. But if you do know about sheaves, it's a good exercise to figure out how to translate what your usual definition is into what we're doing here. But before that, I want to do an example first, which is not completely it's not exactly this stuff, but it's important. So let's suppose that we have S is k of x0 to xn, and I contained in S is an ideal. I'm mostly interested today in the case where I is homogeneous, but in fact, what we're talking about right here in this example doesn't really matter a whole lot. Okay, or we're letting M equal a finitely generated S module. So I often will do it in terms of S. I will say things in terms of M, but I oftentimes in my mind first run through, I always replace it with S mod I. Obviously, sometimes you can't quite do that, but that's what I would like to do. And now I want to consider a free resolution, a free resolution of M, or of S mod I if in that case. And what does this look like? This looks like 0, M, and then we have a bunch of free modules, F0, F1, etc. Now, it's a polynomial ring. We didn't actually prove it in class, but it does end like this. Okay. Well, let's say M. I don't want it to be the actual number to match this. It's just some finite value. Okay. And I actually might say sometimes if it is homogeneous, if it is homogeneous, I'll always take it to be graded. Okay. So let's call these maps delta 1, del 2, up to del M. Okay. So that's a free resolution. We haven't really talked about minimal free resolutions, but if it were a graded free resolution, a minimal will just mean that there are no constants in here. So in other words, it's you could, if there were constants, you could get rid of some of the terms, but anyway, we don't care about that right at the moment. So instead, what I want to consider are the various X modules. Now remember how we calculate X. So we want to consider the xi of M comma S. Okay, this is over S. Remember how we do that? We calculate this free resolution. We just transpose the maps, and we take kernel mod image. That's all that this xi is doing. So in that case, you can see what happens. We're going to have we'll have x0 of ms, x1 of ms, and I'm going to give one number here. This xc, I'll say what c is in a second. Okay, and it's going to keep going. What's the largest one it can be is this one here, fm. Any higher, it's going to be 0 mod 0. So here we're going to get down to xm of m comma s. I haven't said what c is yet, but we have, forgetting that one, we have all the way from here to here. And these are all a bunch of modules. Every module or every ideal has this kind of thing associated with it. And what happens is the following, is that the ones up to the c minus 1, these are equal to 0. This is going to be not equal to 0. If you think about the last one, as long as it's there are no constants in here. But even if, yeah, so at some point there's going to be a largest one which is non-zero as well. Okay, and the ones in here can be 0 or non-zero. So this is just always the case. It's going to be 0 for a while, maybe never, maybe the first non-zero one is here, but you take the first ones. I'm going to actually essentially say that C is the first non-zero one, and then M is the last non-zero one, okay? And then it's 0 after that. Okay, so here, C is equal to the codimension of M. Now remember what this is. This was equal to, we can calculate what this is from the Hilbert polynomial of M, or the Hilbert function, or Hilbert series rather. Okay, so C was equal to the codimension of M, and in that case, it would also be the codimension of I, which is actually really the codimension of it as a 0 set inside of the affine space or projective space. And M here is equal to the projective dimension of M over S. So in fact, there's a theorem that says that the first non-zero one of these things occurs at this point. In fact, this is potentially a reasonable way of computing it. It's a little overkill. But so the first non-zero one is that, and the last non-zero one is this. And definition in some ways, if you want to do it, that M is called Cohen-Macaulay. Called a Cohen-Macaulay R module, S module, called a Cohen-Macaulay S module, if these two are the same. Codimension of M is equal to the projective dimension of M. In other words, there's exactly one X that's non-zero. Okay, so i.e. C is equal to the M above. And these things are, it's amazing how nice these things are. But some of the ones we will come across are, but not all of them. And anyway, this is, if there's exactly one non-zero one, then it's called Cohen-Macaulay. This is not the usual way of defining it. Usually it's defined in terms of dimension, not codimension, and depth. But if you think about it, there's this formula, which I'm not going to go into right now, called the Auslander-Buchsbaum formula, that will rewrite this as that. So, but in terms of resolutions, this is a good way to think about it. Now, in this case, what happens? If I take the dual of this, and let's do it from over here. We have Fm star. And now the maps are now going this way, Fm minus 1 star. So these stars are just basically the same thing, just transposing everything. This is to F0 star, and this is the complex that we're computing X with, right? And this is going to be del M transpose, del M minus 1 transpose, et cetera, to del 1 transpose. Okay, there is no del 0. Now, what is the X1 here? This is X. Actually, in this case, maybe I want to use C now. So in this case, where M is equal to C, is equal to the codimension. I already used too many M's here, so I'm going to just keep using it as M. So this is X M over S of M. So S mod I in many cases, this. And this is the co-kernel of that. It's this modulo the image of this. So it's the kernel of this, which is everything, and mod that. So this is really what you get on that side. Now, what do we know about the rest of this? So any suggestions? This is a complex, right? How exact is it? It is, well, what does it mean for a long exact sequence to be left exact? That a short exact sequence being left exact makes sense, but this is when you have a lot of them, you could break it up in lots of short exact sequences and get that. But it turns out that, let's just think about it. What is the cohomology at this point here? It's the kernel of this one mod the image of this. That's X M minus 1, which is 0. So it's exact here. And in fact, it's exact in every single one of these, even this one. If I take the kernel of that, mod the image, that is X0, which is, in fact, already 0. So this, in this case, this thing is a free resolution of x m, where m is the codimension of s of m comma s. So this would be the canonical module we've mentioned before. And so in the case when it's Cohomology, you have a ready-made free resolution for it with no extra computation. If it's not Cohomology, no, it's a lot more complicated. Okay. So anyway, so as an example of this, we can just take a look at our twisted cubic example. Okay, so here we have the twisted cubic. And here we have, so I here, I'm not going to rewrite it down, but this is the 2 by 2 minors of our matrix A, B, C, B, C, D. So this is the 2 by 2 minors contained in K of A, B, C, D, which I will call S now. Okay. And then if I take this, I get S mod I mapping to S. I can do this as graded or not, but there are 3 generators, and then there are 2 linear syzygies on it. So this was the F1, F2, and F3 that we've done before, and then this is, if you choose the generators right, the ABC, BCD. Okay. Now, what are the X modules here? We can do this almost by hand, maybe. So what are the X modules? So X I of S mod I into S. Okay. So what are they? Well, we take this free resolution and transpose it. So I take this, I map it to S3, map it to S2, and then this. And now I take the transpose. This is the map F1, F2, F3. And this is the matrix ABC, BCD. Okay. And this will be where X0 is computed. This will be where X1 is computed. And this is X2. Okay. Is this okay with everyone so far? Is that so this is just the transpose of this. S star is S. S3 star is also an S3. It's the dual S3, just like in vector spaces. Okay, what are these things? The kernel of this map is 0. So we have X0 of S mod I into S is 0. Actually, we already know that this ideal has codimension 2 because I think we computed it using Hilbert series. So it should be that the X1 is 0 too, but let's take a look. How do you calculate X1 of S mod I into S? You have to look at the syzygies, the kernel of this map here. So you need triples of polynomials such as something times this, something and that, something and then that is 0. And one of them is this exact thing. That's properties of determinants somehow. So if I actually add in, these are the 2 by 2 minors of this, so so you get some sort of 0, but you have to actually check that there are no other elements in the kernel. You can do that how? By using a Grubner basis over the free module S3. But in any case, you get 0. So the kernel of this is del 1 transpose, this is del 2 transpose, this is del 1, and this is del 2. So kernel of del 2 transpose is actually equal to the image of delta 1 transpose. In other words, the only syzygy on these are multiples of this. And then what's X2? X2 of S mod I into S is S2 modulo this. So that's equal to S2 modulo the image of the matrix ABC, BCD. But this is also equal to the co-kernel, but just by definition, of the matrix ABC, BCD, which is that makes this the presentation matrix of this module, because it's generated by 2 things with the relations, 3 different relations, A times the first generator plus B times the second generator, 0, and so on. Okay. So this is the X that we get, X3 and so on higher. So we get by definition, in some sense, if we don't mind using that as the definition, we get that S mod I is Cohen-Macaulay. I'll write CM. That does not mean complex multiplication. For those of you who do elliptic curves stuff, that's Cohen-Macaulay. And this is the canonical module, this thing here. And its free resolution is what? Its free resolution, let's just write it down to make sure we have it all. And the free resolution, or a free resolution, of the x2 of S mod I into S, the canonical module, is, and I can do it the other way. I'll probably just let me just do it this way: x2 of S mod I, just to kind of keep you on your toes as which direction things go. So this has two generators. It has three relations, and the relations have to be a 2 by 3 matrix, which is ABC is the first, and BCD. So AB is the first relation, and so on, just like we were just saying. And now what's the kernel of this thing? Well, by the x being 0, the kernel of this is, in fact, the polynomials f1, f2, and f3, where here f1 is this determinant, bd minus c squared, f2 is negative of that determinant, and so on. Okay? And this goes to S1, or S, and that's it. So this is the free resolution, and we could do it with grading as well. So, but the point is that in this case, we have a very nice description of this thing without any extra work. And unfortunately, if it's not Cohen-Macaulay, for instance, the rational quartic that we've had is not Cohen-Macaulay. It has two different X modules, and that's just the way it is. So it's a harder deal. Any questions? Yeah.
I'm just trying to understand. How do you interpret what the X module is measuring?
That's a good question.
What is each of the
So it's basically every time you do a free resolution, where is the free resolution? It's up there. What you're doing is you're taking all the relations on those polynomials, right? The kernel of it, all the syzygies, and you're writing it down. So, like for instance, f1, f2, and f3, there's two syzygies, ABC and BCD. Okay. And then you keep, so you have all of those are all the polynomial relations that are generated by each one as you go back. Now what you're doing is you're transposing, you're asking, it's a very weird thing, okay? But this is actually at the heart of duality, basically. Serre duality, if you've heard of that, and so on. This is exactly where it all arises from. We'll talk about that a little bit. We're going to talk about some of Serre's stuff. And basically, these modules that I'm talking about here are precisely sheaf cohomology modules. I shouldn't say precisely, but close to it. Okay. But it's weird what they're measuring. I mean, it's very, very explicit. You can say you got some. You know that that thing is that composes to 0, and in fact. Well, the other way, it's the kernel is equal to the image, but when you transpose it, the kernel of this, is that equal to the image of this? Well, sometimes it is still complex. It's the product of two matrices. If it was 0, the product of the transposes in the opposite order is 0 as well. But it's not always going to be exact. And somehow cohomology is measuring that. And these X's are the basic thing. Yep. They do. They have a lot. There's a lot one could say about this. I could give several lectures on this, on these things by themselves without anything else. And I really like these X's a lot. So that would be really fun to do, but then we wouldn't get anywhere.
That's kind of what I'm pushing for. Like interpretationally, all I understand is modules and dimorphisms. So like x0 being 0.
So x0 is so a few things. X0 of any module into S, or into any other module for that matter, this is actually just Hom of M into S. Okay, this is over any ring, and this is totally general.
In the example, S mod I into S, that just tells us there is only the zero homomorphism.
That's exactly right.
From S mod I to S. And then what about X1?
X1 is a little more interesting. So here's one way to think about it. X1 of MS is basically equal to the set of extensions. That's where the X comes from, is extensions. And the extensions are S mapping to E mapping to M, like this. So E is it's the things that can sit in the middle of such a short exact sequence. If one possibility here is S direct sum M. That's the zero element of this, okay? So if this is zero, that's the only thing that can be here. But if it's non-zero, then you can use it to construct this. And that's actually an amazing way to construct new varieties and things, or vector bundles, or things like this. If you can find an element where this is one-dimensional, for instance, then you can pick out one of these guys here, and that gives you something which is oftentimes has nice structure, and you can really go with it. That's one real use in computational algebraic geometry of these X, is if you actually have an element that you can get a vector bundle or sheaf out of it, and in fact, then when you take so-called proj of it, you get a variety over the original thing. So this is how you construct elliptic ruled surfaces and things like that. Once you know that kind of stuff.
So for the example, X1 is zero. So the only thing in the middle is just the direct sum.
That's exactly right. And this here would be S mod I in this case. So, and that's not completely obvious. Even more not obvious is what's the addition onto the addition here. And it turns out that once you actually piece together what this really means, there's an obvious thing. And it goes under the name Yoneda Ext. There's a whole Yoneda did, there's Yoneda's lemma, but there's also the whole X thing, which was done in total generality as well. But this is a very important aspect of Ext. There's another important aspect is you can have a product on these things. If I have an X1 of this M comma M, say, and I have another one, I can get an X element of X2 of M comma M by somehow composing things. And that's again, if I were giving I could give a course on Ext, and but we can't do them all. Okay, but anyway, Ext has lots of different interpretations. We're seeing one that it relates to invariance of S mod I, of the variety. We also have things where we can use it for construction. And then there's another one that turns out to be even useful in physics for doing Yukawa couplings and things like that, which is the product thing I was just talking about. Anyway, there's all sorts of stuff. But right now, I just want to think about it is this friendly amount of information up here. It's not that friendly, but you can compute it in Macaulay too. It's hard to do by hand oftentimes, but it's worth trying it on some things by hand that are not too large. And in fact, on the problems, I have a few examples of where one might be able to do some of that. Actually, those might even be pretty easy. Any questions on this? Other questions, rather? Yep.
In this case, X is cohomology of
It will be of S mod I, essentially. So, in fact, we're going to do that right now, basically. Well, in a few minutes. Okay.
This might get answered, but
yeah,
is there like a special reason why we would just like to note it X here, as opposed to just like cohomology?
If you think of it as just cohomology, that is totally fine. However, then you have to really be so it's a way of presentation, really. So if you are comfortable with sheaves and injective resolutions or Flask resolutions and all that kind of stuff, you can do all this stuff. It's not very computational, though. I think this is the way towards the computation aspect of it. It also gives you more information oftentimes than that. just because it's more explicit and you can sort of see more what's happening. You can certainly prove all the stuff without that. In fact, that's sort of what's done, in the whole EGA thing. I guess they might actually do it this way some. Anyway, so I just want to recall from last time also. Recall from last time how we're thinking about modules, okay, and sheaves. So we take graded S modules. I guess S is as will be most of the time. Right. Yes, question? Oh, yes, thank you. Thank you. Okay, so we take the coordinate ring of projective n space here, the homogeneous coordinate ring, and we take graded S modules here. Let's say M is one of them. Typically, we'll do finally generated. There's ways around that, but anyway, that's what we're interested in. And then you have this tilde operation that goes to coherent sheaves. You can think of this, depending how you define it, you think coherent sheaves or coherent OPN modules or something like that. And this goes to M tilde. Okay. And this functor takes S tilde. If you remember, S tilde is O of Pn. And S mod I tilde, if this is the ideal of some scheme or variety, this would be X if I is equal to the ideal of a projective X contained in here. Okay. That's not true, what I just said. It's not equal to X at all. It's equal to the sheaf OX. Okay. And then we also had that S twisted by some number D tilde. We haven't defined what O of Pn of D is, but if you in sheaf land you can define a notion like this, and it's compatible with this construction in the sense. And also, if M sub D is equal to 0 for D large enough, then that implies that M tilde is 0. Okay, so A, B, C, D. These are all things we did last time. And a very important one, E. Actually, let's do E up here. This one is that the tilde is an exact functor. In other words, if I have an exact sequence of graded S modules, finally generated, say, and I take tilde on everything, I get a exact sequence of coherent sheaves. And that's how everything is obtained. And F is all coherent sheaves are obtained like this, are obtained in this way. And then one of the questions I asked you to take a look at was basically that that M tilde was isomorphic to N tilde. Basically, if and only if MD, so the truncation, sorry, M greater than or equal to D. Remember, this is the direct sum of all M sub E's, where E is at least D. That this as a module, and then this one as a module, that these were isomorphic to each other as S modules, as graded S modules. For some D, and therefore all D for some D. For all D larger than some value. Okay, and basically this is, so that's exactly follows from this and the exactness. But in any case, this is the situation that we were in. Now I want to talk about, so basically we're going to define, so we've defined the sheaf as a module subject to the fact that two of them can be the same, or one of them is 0 if for large enough degrees it dies out. Okay, so an example of that, remember, was if S is equal to K of X, Y, Z, say XY, and this is on P1, for instance, and if I take S modulo XY, This is oftentimes what's called, it's just a copy of K isomorphically as vector spaces, but it's also a module over S. Then this thing K tilde, this thing has nothing in degree higher than 0, and so that this thing is the zero sheaf. Okay, so these things that are essentially Artinian, that are basically are zero dimensional somehow, therefore they're going to be degree 0 and high enough degree, and they're going to not be anything sheaf wise, which is a useful thing. Yep.
The Artinian is somehow dimension 0. Like, should I just think, oh, it's Artinian, so geometrically bunch of points?
No, it's actually not a bunch of points. It's the empty set. So so for instance, what is the zero set of xy in projector in P1? So both x and y would have to be 0. So if it's Artinian, that means some power of each of the variables is in the ideal eventually. So that means that variable geometrically has to be 0. But if all the variables are 0, that can't happen for projective space. So it's the empty set. Projectively, it's the empty set, and that's what this tilde is doing. Is that it's saying that, aha, you know, normally it would be O of the zero set, O of x, but there's no zero set, so it's 0. That's the intuition for why this is true. Or that's at least one indication of it. Does this, so any other questions about this stuff?
Lots, but
Yeah, okay.
time was right.
Yeah, so but we can keep asking. By the way, remember that I am available to talk about this stuff also. Although today I forgot to tell everyone, I told people here but not online, from 2 to 3 we're having a Macaulay 2 session where anyone can ask questions. It doesn't matter how easy it is or involved, but you can also get help installing it or setting up your system nicely or whatever. We'll help with that. Okay, actually I don't want to say much more about that. I mean, I do want to say, I could just go on and on about this, but let's do some sheaf cohomology now. So this is going to be sheaf cohomology. Sheaf cohomology is kind of interesting. If you look at how sheaves are defined, it's on open sets, you give yourself something and so on, and they piece together nicely, and it's a lot of data. And then there's a way of doing injective resolutions of these things, which is what you'll see in Hartshorne's book. That is not the way we're going to be thinking about it at all. But then, even in Hartshorne, he switches it to so-called check cohomology. And that is what we are really going to do here. So we're going to consider for Pn that Pn is the union for I equals 0 to n of U sub I, where U sub I is equal to Pn minus the zero set of xi. Okay, so it's just where the ith coordinate is non-zero. And this is the standard open cover. Now, I want to consider something that's like a check complex, but just algebraically, so we don't have to, I don't want to have to worry about what a sheaf is and so on and do it. But if you know what a sheaf is, you should be able to see that what I'm going to write down is pretty much the same thing. Okay, so let's consider, except actually it's a little different. We'll see why. So let's consider the graded check complex. I'll put this in parentheses. And here it is. I'm going to call it C. It's going to be very simple. Oops, I'll have to describe some of these notation though. This is I equals 0 to n. There's going to be one term for each of the open sets here. And basically what I want to do is I want to consider what happens if I set xi to be non-zero. Well, one way to think about that, here's the standard notation for it. I'll describe it a bit more. In fact, why don't I actually do it here? As sub xi is basically take S and invert by the element xi. In other words, allow xi to be a denominator as many times as you want, okay? So one way to think about that, this is S and you just adjoin xi inverse, which is sitting inside the fraction field of the polynomial ring and so on. So you're just, you have polynomials divided by some power of xi in there. And then you're going to do similar things for x, say I1 dot 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 xil. That's going to be S where you invert by xi1 and all the way up to xil. Okay, these are fairly nice rings, but they're not really nice because this as an this is an S module. It's a ring, but as an S module, this is infinitely generated. Okay, this is as a. Let me write that down afterwards. But at any rate, so these things are kind of nice, but they're also kind of not nice. And they're not nice, very much not nice, because they're sort of infinitely generated over whatever we want to deal with. So here we're going to take direct sum of xi, xj. I'm going to say for all I less than j. Okay, so this is going to be this open set. This is sort of corresponding to the open set ui intersect uj, where you're inverting, but when you can invert by it if it's non-zero on that. So on the open set, this is in some ways going to be some sort of coordinate ring like that. And we can keep going. We can do now 3 at a time, 4 at a time, until finally we get to n plus 1 at a time. But there's only one set of n plus 1 of them. So this is going to be S sub x0 dot 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 xn mapping to 0. Okay, so this is the typical graded, the check complex would be where you take the degree 0 elements all the way along. And I'm not going to do that. I'm just going to consider all of them. And where we have natural inclusions, xi maps into this guy, because if I had divided by xi, that's certainly a subset of this thing. Okay, so we have natural inclusions. Let's say what it is for n equals 2, just to sort of be able to fix it in everyone's brain. Okay, so let's do here we'll do S as k of x, x, y, z. And what is this thing? So it's 0, and now we have a direct sum of 3 things, one for each one of these things. So I'm going to say it's S sub x, direct sum S sub y, direct sum S sub z. Okay, is everyone okay with it, what these things mean at least? Okay, and now the next one is we take every pair. So that's going to be S sub, do I have an order? I don't care. X, y, you invert both x and y, or you invert both x and z, or you invert both y and z. Okay, and we'll say what the map is in a bit. And then the last term here is where we invert all 3. That's S sub x, y, z, and that goes to 0. Now, what are these maps? I'm going to think of this as a block 3 by 3 matrix that takes elements of Sx to any one of those things. So the way I think about this is here is the elements of Sx, the elements of Sy, the elements of Sz are going to go to the elements of Xy, Sxz, and Syz. And then same here, we're going to have 3 columns and 1 row, X, Y, Z, and then here is S, X, Y, etc. Okay, just these 3 things there. And I probably should have moved it down a little bit low. But what is the map here? Sx is going to go to 1 here and a -1 here. And 1 just means inclusion. It doesn't mean the identity, because that would be the map from Sx to Xy, Sxy. So an element in here will map to, so an element in here, some fraction, a over x to the r, x cubed, say, would go to a over x cubed, comma, minus a over x cubed, comma 0. Okay, so that's all that is. And then the next one, where does y go? Well, it is only going to, it can't go to xz because it's got an inversion by y. So here we also have to, we just have to choose the signs consistently so that we get a complex in the end. And that's fairly okay. So here we have these ones is what I've chosen. And if I do that, here are the signs that I'll get here, 1, -1, 1. And the 1 means the inclusion map. Okay. So does everyone understand this? This is really what the check complex is always defined as, with exactly these kinds of maps. It's just a question of what's here, and so on. But this is an algebraic way of looking at this. Okay. So I'm going to call this C, which depends on what ring we're in, but it actually doesn't, as long as we choose all the signs and this thing set, it is actually a fixed complex now. Let's go over here. So if someone, maybe if we can switch that camera. Okay, now here's the thing. So these things are, by the way, complete. Is this a map of graded S modules? Is each one of these things a graded S module, for starters? If I localize at X, is it graded? Actually, it is, because I still have some homogeneous thing divided by some power of X. So note. So S of X is as an S module. What is its generating set as an S module? This is probably a good question to make sure you're all on board with this. Is generated by what? So remember, this is just S, and I'm adjoining X inverse. Maybe I should use Xi, but let's use Xi. Okay. So what is it? Well, as an S module, there's the element 1 is in here, certainly. And that gives me any element that's actually in S without having divided by that. Or I could divide by X1, and then I get everything that has a denominator of X1 times anything. Or I can divide by X1 squared, or I can so on and so forth. So it's generated by an infinite number of guys. Or is it? Once I have one of these guys, all these other ones are in it because I can multiply it by X1, which is in S, and it will be in here. But it's still infinitely generated. So this is infinitely generated as an S module, which is kind of annoying. Okay, but nonetheless, it's okay. But every single one of these things, I can write down everything that doesn't. And this is completely graded. I can actually write down. I can take a homogeneous polynomial divided by X1 squared of any degree, and that will give me all of the terms. It's an infinitely generated kind of graded module. So this is graded. In fact, the degree of f over x to xi to the r is equal to the degree of f minus r. Okay. So each one of these things is, actually, it doesn't matter whether you divide by a single x or multiple of them, it's still going to be the case. I'm just going to have 1 over xy there and 1 over x squared y squared and so on. So I get this thing. So this C, so all the terms of C are graded. And how about the maps? Well, they're the inclusion maps. They go from an element to itself, basically, or something itself minus some other thing. But they're all the same exact degree. So this is graded, and the maps of C are graded of degree 0. Okay. Yes.
I'm just going back, confused.
Yep, sure.
How this is exact, the middle term. So like.
I didn't say it's exact.
Oh, you didn't say.
No. This is a complex. Yeah.
It's not.
It is. This particular one is exact, but yeah, that's right. So
for example, again, so you said f over x to the r goes to
So f over x to the r, zero, f over x to the r goes to where? It goes to the element, it's a vector in here. It goes to the element f over x to the r here, minus f over x to the r here, and 0 here. Okay.
and that's just like because of the way that the standard affine opens glue together. Like this, I'm trying to understand this.
Oh, so you would have liked me to give the actual map here,
Yeah,
but basically it's
I'm just confused by the sign. That's all.
yeah. So I didn't actually write that down, so I will probably screw it up. But basic idea is that you're going from here to here, so you have to say what the element is in that spot there, and it's going to be a sum over -1 to the all the number of spots that you're in. So it's sort of like exactly what you would do for a simplex in algebraic topology, or it's sort of, but it does actually the exact map should be stated. Okay, and I did it for this case, but I haven't done it in general.
Okay, you're saying this is what it is, like for that specific example.
Yeah.
But the details are. So
yeah, probably I should. I will probably try to. I'll give you the other thing for.
I haven't learned about this before. So
Yeah. Okay. Are you familiar with Koszul complexes? No. How many people are not familiar with Koszul complexes? Yeah. Right. Okay. Okay. Anyway, so it's the same kind of story, but we're not going to worry about that right now, because we haven't done that yet. But anyway, we have this thing, and now the idea is we're going to make a definition. So we're going to consider a module M, a graded S module. Actually, let me make sure I'm doing this in the way I want to do it. So I'm going to define two things. So I'm going to define HI. Sometimes it goes by the name Pn, comma M tilde. Okay. But I typically leave out the Pn because it's doesn't really matter a whole lot. So I oftentimes will just use HI of M tilde. So this is the ith cohomology group of this sheaf. And what this is, by definition, is this is the ith cohomology of if I take C and I tensor the whole thing with M. Okay, so what does that mean? Tensoring with M is actually a really simple process. What it means is that if I tensor this with M, I'm just replacing all these things with M's. I have 3 copies of M. One of them I get to invert by X, one I get to invert by Y, and one I get to invert by Z. I have 3 copies of M here, and I've done some inversion. These are not necessarily inclusions any longer, but I still get natural maps between them. And then I do that here. And then I want to take kernel mod image of that. That's what the cohomology here is doing. But in fact, what I want to do, and I didn't give myself quite enough room. Let me say this again. What I want to do is circle and move it over. But this is equal to HI of M tilde. I'm going to just get rid of that in a second. And this is if I take the complex C tensor over SM, and I take everything in the degree 0 part of it. So if once I do this, tensoring with M doesn't really change. Okay, the grading, M is graded and everything, but this is still a graded thing where all the maps are degree 0. And I can take the degree 0 part of it. That means take the degree 0 part of every term, and then this is going to be a complex of vector spaces, of K vector spaces. Is it finite dimensional K vector spaces or infinite dimensional K vector spaces? Alas, sadly, what are the elements of degree 0 even on this one? Well, 1 over x is not degree 0, thankfully, but y over x is. Y squared over x squared is. Y cubed over x cubed. All of those are degree 0. So that thing is not finitely generated. So it's infinite dimensional vector spaces in there. So that turns out to be computationally kind of annoying because how do you compute it somehow? But at any rate, so we have that. That's the definition of the sheaf cohomology. I take this complex over here. I just replace all the s's with m's. I still allow myself to invert by the x, y, and z in the appropriate places. I take the degree 0 part and I get that. So this is definition A. Definition B is, well, it's kind of nice actually, and this is one of the advantages of not doing sheaf cohomology directly. Then you can see that if instead I could do hi m tilde, and I'm going to call it lower star. And by definition, this is a definition here. This is hi of C tensor over S M. This thing is a graded S module. Okay, does that make sense? I'm not saying that it's a finitely generated thing. In fact, this is making the whole thing look kind of depressing. You have to be pretty good optimist to think that this is going to give you anything interesting. Okay. So does this make sense? So here I'm not doing it, I'm just replacing those with m's. I get a bunch of modules. I take kernel mod image, and that gives me the ith cohomology. Okay. Yes. Yes. Star. So there's no degree 0 part. This is just the whole module, and you're not just slicing it 1 degree. Actually, since it's graded at degree 0, it is true. So note that what happens is that I lower star of m tilde. Okay, this is this thing. Here, just a second. This is the direct sum over all d in z of hi of m tilde of d, because the degree 0, if I shift m, all I'm doing is taking a different degree part of this complex. Yes.
I think the thing that you were wondering about is it looks like you've said that hi of m tilde is equal to hi of C tensor over S of m, and then you wrote later down that's the degree 0 part, but now.
Oh, I see what you're saying. Absolutely. Yeah, thanks. I totally misunderstood what you were saying. I forgot, I said I would erase this afterwards, and because I didn't have room to put that in. So this is what it is. So this one is, you just take the degree 0 part. Actually, and what happens of here, if I want a different degree part, like degree d part, then I'm just getting of the shifted degree m tilde of d or m of d tilde or something like that. So I don't know how to say this, but this is kind of okay. This is a definition. We can actually work with it because it's mildly infinitely generated, but it is infinitely generated. Okay, so the question is how does one actually compute these things? So suppose I actually let's even forget. How about the first case? Is that m is equal to s. In other words, m tilde is equal to O of Pn. Okay, and then that means that we want hi of OPn maybe twisted by some d for all I and all d. Okay, this is what we would like to compute. And this is something Serre did. And Serre just rolled up his sleeves and computed it. And when he did that, he said, oh, and then he was immediately led, at least this is my interpretation of what he did, because he didn't ever tell me this. He said, but oh, I know how to do that. And I see how to do it. And actually, I see how to actually compute these things for general sheaves or general M. And I see how to do local duality, which is the Serre duality, essentially, or one of the forms of it. And it's actually a really good form of duality, which is actually not in Hartshorne, which is kind of unfortunate. But at any rate, so I guess the first thing is, we would like to do this. On the worksheet, I have for you to try this for this case here, for this n equals 2 case. I mean, just have to calculate this for any, so in degree 0, for instance, but also in any given degree. Okay. So how would you even do that? And I have a hint in there, but can you imagine how you would compute the cohomology of this? I mean, just the kernel of this, mod the image of that. I mean, here's something that you have going for you, though. All of these things are generated over S or over, actually, even over K as a vector space. This is a vector space over K, and it's generated by monomials. Well, the monomials have negative exponents, some of them. And same here and here. These are all just a bunch of monomials. And these are too, and these are, and we're not changing which monomial we're talking about. So if I take a monomial here and I map it in, I just have the same monomial, essentially. So in fact, I can take this whole thing and just break it up. It's a divide and conquer thing. Do it for every single monomial. And then I get a nice finite dimensional vector space over the field that is essentially going to look sort of like this. And then it's going to be really easy to compute. And that's basically what Serre did. So here I want to write down what the result is. But I think it's better for you to actually try that and see how it goes, because it's really not so bad. I don't think you would actually see that proof if you read Serre's stuff, but I mean, this paper, this is all this fact paper from 1955. It's just an absolutely amazing paper, at least the last part of it, which does all this stuff. It starts off and it defines what a graded module is. Okay, you say, oh, I know what a graded module is. And then it goes off and then it does another thing, which is some trivial refinement of that. And then the next section is some trivial thing based on that. And you're just like, oh, this is just like, I mean, what's he doing? He's just like playing around, not doing it. And then all of a sudden, somewhere along the line, he's done something really deep. And you're going, wait a second, how did that happen? And it's actually, that's the way he writes, but it's very cool in many ways. Anyway, let me give the theorem here. I need a little bit more room for it, though. By the way, right now we're doing this. This is all from like essentially the 1950s, right? Although I don't think it was ever noticed as that until much later that you could actually compute with any of this stuff. But what I want to do later in the class is I want to do more modern views of computing sheaf cohomology using the Bernstein-Gelfand stuff. But for the moment, we have to get more into it like this. So here is the basic theorem, or this is Serre. This is in fact 1955. So here is the result. HI of OPN of D is equal to some number of cases. So what is it? Well, if I is equal to 0, okay, that's going to be right here. I equals 0 is you take the kernel of this map. There is no image. So it's just the kernel of this thing. And what is it? Well, it turns out to be the degree D polynomials in S. So S here is K of x0 to xn. And that's for any D. If it's negative, it's 0. Okay. And now if I is between 1 and n minus 1, it's just the 0 for any d. And then the interesting one is the top one. So what happens if I is equal to n and any d? Well, it turns out then it's s, the k, the s, the dual vector space here in degree. Actually, let me put it this way. It's in degree minus d minus n minus 1. This is a vector space. Okay. Might be 0, but it's a vector space. And I'm going to take the k. This is the k vectors, the k vector space dual. Okay. So this is what he proves. He actually does it more generally. You can do it over any ring here and things like that. But it's all the same proof. So this is what this is. This tells us something. Let's actually just parse this out a little bit. So what is, if I take Hn of OPn, which one, what is the, if this is 0 for a good number of things. So let's say d, this is equal to 0 for d. Well, it's going to be equal to 0 whenever this number is negative. Okay, because there is nothing in S of negative degree. So when is this negative? That's going to be negative if minus d minus n minus 1 is less than 0. That means d has to be greater than minus n minus 1. So for d greater than or equal to minus n, this is 0. And then also what it says is that Hn of OPn of minus n minus 1 is equal to, that's it now a 0. So this is a single vector that has dimension 1, basically. Okay. So this is the basic computation. And once you have this computation, you're not quite there yet, but you have pretty much what you need to get going. So now what I want to do is just say a couple of the other properties of this. And then in some ways, once you have that, you can get by with quite a lot. In fact, this example, for instance, without knowing anything else. So anyway, I guess my point is that this, if you don't mind this definition, and it is true, we have to be careful about what the signs are in the definition here, okay? But it almost doesn't matter as long as it's a complex, okay? But as long as you do that, then you have a definition and you get the things, and now we can start computing these things. These things are all vector spaces. And so what are some other, here's some other basic facts about H of Hi of M tildes. One of them is the long exact sequence. Okay, so suppose that you have, if we have 0 is, I'm going to use A's and B's and C's here. A tilde, B tilde, C tilde is 0. Okay, where A and B and C are graded S modules. In other words, I want them to just be sheaves. This isn't, by the way, just on projective space. This works for anything in any projective variety or something, because these things might be anyway, this includes all of that case. But anyway, so here we have, if this is exact, sorry, I didn't say that. If this is exact, okay, so the kernel is equal to the image at each point. For instance, if it were exact a sequence of modules, and then you just tilde it, that's fine as well. Then there exists a long exact sequence in cohomology. And how does it look? Well, it looks like 0 goes to H0 of A tilde. Actually, you can either put the star there or not. It really doesn't matter. This thing goes to H0 of B tilde to H0 of C tilde. And now this is it turns out that this H0 thing has this left exactness thing going on. And now this goes to H1 of A tilde, H1 of B tilde, H1 of C tilde, and that goes to the next one, and it keeps going. Okay. By the way, how far can it go? How high can these HIs be non-zero? These are all vector spaces. They might be infinite dimensional vector spaces at the moment. We don't know, but they're all vector spaces. But in fact, if you think about it, once we're past this point here, it's going to be zero because the cohomology, no matter what, the current line image is going to be zero if you're past this. And this has length. This is the 0th spot, the first spot. This is the nth spot. So maybe I should say that HI, I'm going to just put PN here just because the n is important. This is equal to 0 for all I greater than or equal to n plus 1. As soon as you're past that, you always get the 0 thing. Here's something else that if we were to prove the following the other statements that we're going to do that are from Serre, this would follow, but it's actually an important thing. HI of Pn, comma M tilde is a finite dimensional vector space for every I. Okay. This is not obvious from this, and in fact, if it's not a projective thing, it's not true. So this is something that if you ever taken a class on curves, like from Fulton's book or something like this, or if you ever do, they prove, and they spent a lot of effort to prove that this one space of functions is finite dimensional. And guess what? This just immediately drops it in your lap for not just in a totally much more general situation. But this turns out to be pretty good. By the way, so the same thing holds if you put stars on it, but HI, lower star of M tilde, is not necessarily finitely generated as an S module. A lot of times it is, but there are cases where it's not, and we have to probably understand that. Okay. So at the moment, I think, yeah. So I think what we're going to do is we're going to first we're going to take a break, and second we're going to work on we can work on a couple of the problems here. However, I was also thinking I wanted to talk about quadrics, 4 quadrics and their Betty tables and stuff like that. Did anyone get a number of Betty tables? Did anyone do this problem or play around with it at least? Well, then maybe that's one of the things we'll do in the next hour, because and I will, after break, maybe I'll spend a few minutes showing you how you can do it in Macaulay 2. And so we'll take a break from this for a bit, and then later on we'll finish. There's not that much more to say about this, as long as you, I mean, basically, as long as you give this definition, everything we're going to say is actually provable, but would take some time, some of it. Okay, but it's not. But there's not too many other ingredients. But the quadrics thing is kind of interesting. I had said, oh, do the 4 one first. The really interesting one is 5. Not so. The 4 one is actually quite interesting, and I don't know the answer yet for it. So, but I have an idea. But we can play around and see it. Did anyone online do the quadrics problem? Fair enough. Okay, so anyway, we'll take a, let's see, it's 11:10 now. Let's start up again. Should we give it 15 minutes? Probably that's a good idea. So 11:15 is 25. 11:25 we'll come back here and we'll play around with quadrics for a while. And then either we'll go back to this or I'll have you do the first couple problems. Probably better to get the first couple problems along this line done as well. But we can decide that at that point. Okay, thanks. You're all welcome to bring a lunch in here and have it during it too. At least as far as long as that's allowed in the room here. Yeah.
I'm not, so you mentioned that there's some trouble computing S at xi because it's infinitely generated.
It's just it's infinitely generated as an S module. It's infinitely generated as a vector space. But it's finally generated as an S sub X module.
Yeah.
So, but the trouble is that here you're mixing different rings. So things are finally generated with respect to different rings, and that kind of causes confusion, I think. In fact, it can be very confusing when you're actually trying to do this and you're doing this in an infinite thing, but it really should be finite dimensional. But yeah. Yes.
Really a bit, so we're doing some catch up, but is it at all clear why that definition is independent of the choice of M that you use for M tilde? Because we talk about like the different M's can get you the same.
Actually, it sort of is because once you invert by these things, you're making them the same. As soon as I invert by any one of these things, M sub xi and M something else sub xi, should be the same thing.
Shows the differences because like
Yeah. Actually, I have to make sure. So it depends if you, there's another aspect of it that we might talk about. But I'm pretty sure that that's the way you would want to think about it.
okay, that makes sense because like if you're 0 in all the time degrees, if you go down and then go back up again, you have to have been
Exactly. So if M is 0 in high enough degree, then sub xi, yeah, you move it.
You move up and then down. Shows you that.
Yeah, that's right. It has to be the same thing by definition of what this means, and that means that that M sub xi is actually going to be 0 as a model.
That makes sense. I just never thought about it this way before because I just I do the sheaf cohomology.
Yeah, right. So it's
It's immediately obvious that it's
it,
you don't even touch that.
right. On the other hand, this does give you an advantage over that,
Which is you can actually
is that you get the module structure on this thing. Whereas otherwise you have to prove that you have, when you go from hi of M tilde to hi of M tilde twisted by something, by multiplication, you can multiply by a polynomial and it will go into the next thing, and that's a well-defined module structure. So you would have to prove it, whereas here it's just automatic.
Don't you just win by functoriality for that?
Do what?
For the normal definition of sheaf cohomology, don't you just get that by like functoriality of the multiplication maps? on the.
You have to show it's
the functor.
commutative. So do you get that from functoriality?
Yeah, it's a functor, so if you apply it to any diagram, everything, right?
That's true. So I guess that's right. If you go F to F, you multiply by something. Here you multiply by something here, and you go the other way. And then you'll get the functor. Yeah, so you have, that's right. I guess it is true.
This
So-
is nice because you have to actually do with it still.
It's nice because this gives you a way of getting the entire module, which is for constructions that I was talking about, turns out to be useful. Actually, it's useful in a number of ways, because when you're actually constructing, like if you're in the case where you want to actually construct surface equations of surface and before, for instance, you need ways of getting ideals, and in order to do that, if you need the module structure on these cohomologies, and somehow that means the free resolution. You just want to think about it that way. So it's otherwise it's all the same. Yeah. Yeah.
What is the relation between the cohomology modules with the underlying topological space? Or
Yeah, that's an interesting question. That's much harder. And the reason it's much harder is
Like smooth
so
it out
how do
so
you
it's straight.
even define it? So you have to start with some triangulation of the variety. Or something
There's no,
like that.
like, so you know the polynomial, so you've got.
So actually there is, so the way you get it, so suppose you want the integral singular homology. Okay, how do you get it? Actually, I don't know of good algorithms for doing that, but I know how to get it sometimes. So for instance, yeah, what are some of the things you can do? One of them is you can do Hodge theory. So so you can calculate these HPQs, and then those are actually sheaf cohomologies. And when you sum up a bunch of them, you get the dimension not over Z, but over the complexes of the integral homology. So, or cohomology. So you can get it that way. And in fact, that's really that you completely don't see the torsion that way. Okay. But that only works for smooth varieties. Okay. So so if it's singular, you have to do something else. And I don't know of a good way of doing it in general. In fact, even for
I was missing something.
yeah, no, it's actually it's tricky because here's the thing is that if I look at Z, it is actually, I can think of it as a trivial sheaf over any open set. I just set it to be Z. So it is a sheaf, but it's not a coherent sheaf. It's not coming from a module over the polynomial ring. And so all this method just fails. So this is not for every sheaf on projective space. It's only for sheaves that come from modules, which happily are many of the ones that are most interesting. But there are a lot of others that are not. So and one of them is the integral homology. And so one way to do it is to actually triangulate the variety as something over the complex numbers, but I don't know how to do that. If I have a reasonable size thing, I just don't know. Yeah,
Oh, yeah.
it's dimensional explosion, and yeah, it's really it's tough. It's tough. I would really like that. Good way. Which problem?
That I did as a PhD student 50 years ago.
Yeah. Do we have time now?
Oh, yeah.
I don't. We have 5 minutes, but
It's-
yeah. Here, let me get my water for a second.
Arrows came from physics and the sort of analogy, Feynman diagrams, twister diagrams. But anyways, you don't really need to know what a twister is, but so that's a projective space.
Mhm.
That's a dual projective space. Okay, so we have 2n just dimensions here. So you draw diagrams like this. So if this, we call this
Yeah.
X or this Y,
Yeah.
then we're eliminating. So this is
Wait, so what are these things again? This is what?
complex.
That's a projective space, yeah. And what's the other one? The
It's a
dual?
dual,
Yep, okay, good.
but it's still the dual. Is
Yeah,
same,
sure.
you know, it's a manifold of the same.
Okay,
Okay, so now you're then going to subtract the set of all, you know,
Configuration space.
I think of it as dual or just.
Oh, yeah.
product.
yep, okay. Right, so that's the,
Okay. So you're just eliminating.
Yep.
substitutes.
yep,
Now, problem is what's in the topology or the homology
I
of
see.
the ambient of this space, okay? So you want to know this
Hmm. Yep.
space, what is that? Okay, now. And so you can make these more complicated. You can have two. So you eliminate that, you eliminate that, you eliminate that, you eliminate that. Okay.
So,
it's
so
square.
this is one equation here from X,
Yeah.
Y, and this is another X times
Every
Y
line-
prime.
Every line is a hypersurface.
Yep, okay.
So this, so what's,
Oh, wait, even here you get, these you take the hyper, so you're taking
taking
always out,
four.
you have a set of
It's always-
variables, each one, and you're always taking that thing minus,
because
is, actually, it's the 2 by 2 no, you're taking the hypersurface, so it's that vector times that vector,
and
okay?
you know, and the reason this they had to do with integrals where the denominators were like W. Okay,
Yeah.
so the denominators had things like this in them. Okay,
Yeah.
so there were, you know, and there was some function up here.
Yep,
Okay, so now you're doing complex integration over this high dimensional space,
Mhm.
but you have to avoid the singularity.
right,
Okay. All right, so, so the thing of interest is the cohomology, singular homology in kind of half the dimension. So,
yep, right,
so,
right.
at any rate, so the relevant singular cohomology group for this space is Z. This one is Z. So I found one, which was like the K through 3 graph.
Uh-huh.
Okay, so you're subtracting all those hypersurfaces.
Right,
And I found that the relevant group was this,
uh-huh,
okay,
okay,
which disproved a conjecture, because the conjecture was they were always,
right, okay,
like there was one cycle.
right,
All right, so I could find one of these, I could actually construct it as a submanifold. I could never find the other one, and I always thought, did I make an error? You know, like, did
I
I
see.
actually?
that would be kind of a cool thing to, this is actually related to some stuff I've been looking, it's not the same, but it sort of has a similar feel to it. But these are kind of interesting things. So now, this is, when you're looking at the complement of something,
Yes, it's an open set, but you can convert it to an algebraic variety, algebraic variety. Because you can kind of take these products and divide the coordinates, so you're taking like the tensor products, like you're dividing by these. So the division is good because you know, excluded that. And you get some very high dimensional.
I see.
It'd be like the product of the dimensions of the spaces. Space you're dividing by.
Oh, that's actually kind of weird that it would be that bad. But um, shoot, where is it? Here, let me just do fields. So so the maps are actually quite easy to write down. What you have to do, well, maybe I shouldn't write it down now.
Oh, is this for this guy here?
Yeah,
Yeah.
the map is pretty easy. You have an element here, and you want to know what it goes to here. So that means you need to know what the coordinate is for this one. So you look at all the coordinates here, and you remove one of them. It's going to be the one over here, and you just take -1 to the, as you go to each one, it's going to be +1 here and -1 here. It doesn't matter if you do a global change of negative sign somewhere, and then you just do that. But that's the intuition. But then you have to actually write that down as a formula. I always found it confusing to write down, but it's not really that bad. Let's see, let me find the Zoom link here. Where's the Zoom link? Here it is. Oops, I have to make sure I delete all this stuff. I mean, not delete it, but I keep all the okay.
I didn't get as much as I thought. That's spooky. That's spooky.
Where is it? Don't see it. I see, that's why. See, if I'm over here, do I not get to see it? Yeah, you do get to see it. Okay. Can everyone see this here?
Yeah.
No, that's really small. Yeah, right. Okay, let me make it larger. Is that readable? Maybe one more? Let me get rid of this. Oops, that's not what I want. Wait, what am I doing here? Okay. I think now I have everything here. Let me see if this works. No, not working. Too small. I can't. Oh, I have to choose this thing here. Okay, it did do it. Okay, good. Well, this one is supposed to be in Macaulay. Wait. Now this one is supposed to be in Macaulay 2 format. I haven't quite figured out why it isn't. So maybe I shouldn't use this. I thought I would try to do it. Okay. So here, so is everyone back around? So I thought we would just talk about generating ideals generated by 4 quadrics. So here I'm going to do it in 6 variables, A through F. And I'm going to choose 4 random polynomials of degree 2. And then here, let me actually not do this line yet. Let's just do that. Here's what that ideal looks like. It's kind of a bit of a mess, but here it is, like here. And it's long because I set the print width to be 0, which was maybe a mistake. So maybe I'll set it back. Nah, we'll leave it like that. Anyway, it's a bunch of quadrics. So what is the resolution of 4 quadrics that are random like this going to be? So I can take C is equal to the resolution of that ideal. Did I give it a name? I did. I called it I. So resolution of I. And I get this thing here. And it's 1, 4, 6, 4, 1. Okay. This is actually what turns out to be what's called a Kazul complex. It's going to be something, so here I can do Betty of that, Betty of C. And this is what it looks like. There are there are 4 quadratic generators. So that's what this 4 is doing here. And then there are 6 quadratic syzygies on those, which in fact are all of the casual ones, all the trivial ones. You take every pair and you just shift it around. And then there's 4 next, which turn out to be the trivial ones on those. And then one last one, which is the trivial one on those. So this is, if I just take a random one, that's what I get. Now what I want to do is I want to try doing a whole bunch of those. I'm going to make a function called random quadrics. Okay. Here. Oops. And I just did it here. I'm pasting it. Oops, that is not good. Let me do this so I can actually see it. Okay. Maybe this is a bad idea of how to do this. Is this understandable, or should I go back to the Emacs thing? So random quadrics is a function. It takes 2 arguments, R, which is going to be a ring, and number of generators. And basically it takes for I from 1 to n gens, that's the number of generators. You make a list of a whole bunch of polynomials, that number of polynomials, random of 2, R is a polynomial, and you make an ideal of it. Okay. So it's just an ideal. That's a function. So if I run that, it just gives me one. And now if I type random quadrics, it's hard for me to see. That's blocking everything I have here. R comma, let's do 4 generators. Okay, it gives me an ideal here, and I can do Betty resolution of that. Oh. You know, this is really too annoying at a small size.
You should enter the cells, ahead of time, clear them. Then execute.
No, I didn't want to do that because I wanted to show it, because then it just sort of blows through it and stuff like that. But I do agree that that's probably a better way than this. Yes.
Is there a request that we go back to the Emacs stuff?
Yes, please. Okay, I'm going to stop sharing this, and I'm going to share my Emacs, which is where, let me make sure I have it. I'm going to change the size of it. Okay. I have to work on that, but at least it's No, I know, but I wanted to I think well, I don't know. Anyway, let me share my screen here. And this is the one I'm going to share. Okay, now can you see that? Is that large enough? Okay, what I'm going to do is I'm going to put it, that's going to be not good. I'm going to put it like this. Okay, so here I can, I'll try to do is, I don't know how to, sometimes when I give these things to Lynn, they don't make it here because I think that of the .m2 is causing some problem with being put on the web. So I have to talk to her about that. Anyway, and so here is our polynomial ring. Okay, oops, let me restart. Okay, here is a polynomial ring. Oops, I'm running in a version I don't want to be running. Oh, I see what I'm doing. Okay, wait a second. Wait a second. Control U, F12. I just want to go there. I want to restart. Okay, I think now I'm okay. So I'm going to restart again. Oh no, I see what happened. Control U, F11. Okay, now it's good. Okay, sorry about that. Okay, there's our R. Here's our ideal that's generated by 4 random quadrics and 6 variables. Actually, each one is pretty long. And if I look at its free resolution, I get the 14641. That was a random one. Random is I'm doing this mod of a prime number, Z mod 32003. So yeah, what it means is for every monomial, I'm choosing a random number in Z mod 32003. It could be the 0 element. That would happen every now and then, but then you would get a polynomial that is mostly non-zero. So it's mostly quite dense. And so here's the function. This random quadrics is the one I tried to do on the other line, where we actually do the
Random to R.
that gives a homogeneous degree 2 polynomial in R. So for instance, we can actually do this. If I do a random, if instead of that one, if I do random of degree 1 in R, okay, I get this, which is a homogeneous linear polynomial. If I do degree 2, I can do that. Let's see what it looks like. I get a polynomial that actually the print width is kind of messed up because I increased the size of it before that, but it goes off and so on. It's done balanced. So the numbers are going from essentially negative p over 2 to p over 2. So it turns out that if you are doing things modulo p, but you're really thinking of it over the rationals, that's a much better way of doing it. Okay, so now here's the function that just this for loop is that this thing takes it's a for loop like normal programming languages, except the word list, right? What does it do? It allows you to create it makes a list of all the results. Okay, so for instance, if I do the following here, let me actually do an example. If I do for I from 1 to 4 list, and I take the polynomial a to the I, okay, what do I get? I get a list. Lists in Macaulay 2 are curly braces, not square brackets like they are in Python, a couple other languages. Okay, we don't use square brackets on purpose because we want to be able to make polynomial rings, and that would just cause a problem. Okay, so so now this one is actually taking a random quadric, and then it's doing n gens number of them, whatever n gens is that you give it. So this is the standard way of defining a function. Here's the name of the function. You're setting it equal to this function here, really. The function takes 2 arguments, r and n gens, and returns whatever it returns. Here, let me make this larger. Okay. Is that a little better?
No, it's not.
Yeah, I know. So I'm going to fix that. I'm going to put this like that. Okay. But except I might want to put parentheses around it just so that okay. So now if I do that, I have this thing here, and I can try it. I can, instead of doing that one, I can do random quadrics. We can do a smaller ring. How about 101 of x comma y? I'm using different variables than the a through whatever. That ring, and I want number of generators, maybe 2 generators. Okay. What do I get? I get 2 quadrics in x and y. And it's an ideal of them because we put the word ideal here, which makes it into an ideal. Okay. So what we can do now is we can run it and get an ideal in four generators in R, and we can look at its resolution, and we get this 4641. Okay. So this one that's what happens if you get what's called a complete intersection. That means when the zero set of all 4 of those polynomials drops the dimension by 4. It turns out that this is going to be what you get. And it turns out that that's what happens randomly. Okay. So in fact, we can try to see how random it is. I'm going to set a random seed here just so I will always get the same answer. But now I'm going to do 1,000 of them. And I'm going to do this. And I'm going to take Betty res of this thing called 1,000 different times. Okay. So if I do that, what do I get? It's taking a little longer. Oh, wait, I got a lot of Betty tables. Okay, so this returned a list of 1,000 Betty tables. Okay, so in here you can sort of see some of them. Actually, they all look pretty similar, 4641. Okay, so in fact, I'm going to tally this guy. Tally of a list will say how many times each thing occurs. So it'll tell you how many times each Betty table occurs. And so, oops, where am I? So if I do, O is the previous list that we just did. I do tally, and 1,000 of them are 14641. Conjecture, it's always this Betty table. I mean, we did 1,000 of them. That's pretty good evidence, I would think. But the trouble is that they're just, you know, what's happening is you're on some big parameter space where you have 4 polynomials and each one is like a different coordinate. The coefficient of each one. So you have a ton, you're in like a 60-dimensional space or something like that, maybe even higher here. And what do you have there? Well, that means that you have a subspace of that where almost all elements in that huge dimensional space are going to be like this. So to be on a subspace of it is going to be a vanishingly small number of cases. I mean, you'd find it if you do enough testing, but instead what we're going to do, first of all, we're going to switch to a lower ring. If you remember correctly, if I do describe of the ring I was in, it was over 32,003. So now I'm going to do it over Z mod 3, although maybe I'll do it over another one later. And I'm going to do one random quadric, and I'm doing that. And sure enough, even here, where I only take 3 choices for each thing, I'm still getting that. So let's do a set of random seed again, and then I'm going to just do 1,000 of those just to see what we get, just like we did before. Takes a little bit of time. Okay, I don't know what I get, so we have to tally to see. And even here, they're all the same. Conjecture, this is all we get. But that can't quite be right, because if I take polynomials x squared and then xy as 2 of my things, I'm going to get a linear syzygy. And here I don't have any linear syzygies. This dot here is saying I don't have any. So there are definitely other things that can occur here. Okay? So now we're going to try to use sparsity. Okay? Before we're just taking arbitrary polynomials. So what I'm going to do, I guess I'm doing it in Z mod 5 here. Here I take the basis of all quadrics. Actually, there are 21 quadrics, 21 monomials in degree 2. And I'm going to just make a list of that. So this is a matrix. So if I do entries of it, I get a list. And if I flatten, I get a single list. So this is just a list of all the monomials. Okay? And for instance, what I want to do is take this tally of apply. So apply of this, I'm applying 100 times, I'm going to call this function, basically. I'm not using the I, each one. It's just giving me a random value. And sharp sign B, what is sharp sign B? That's the number of elements in the list B. Okay? So random of that is giving me a number from 0 to 20, inclusive. Okay? And so if I take 100 of these, how many do I get? I should get a whole lot of numbers between 0 and 20. And sure enough, I do. The first one is what the number was, and the second one is how many times it appeared. Doesn't look that random. 9 appeared once, 12 appeared 8 times. You have to be the judge whether you think that's I don't know if any of you have taught statistics yet, so you could see if this is random. You'd have to do it more things. Anyway, it's relatively random. Okay. So now what I'm going to do is I'm going to make a little function here. Oops, I'm going to do this a little differently so we can see it all. It's called random sparse. It's going to take this matrix, this list of monomials B, how many generators I want, and how many terms I want each one to be. So what I want to do is I'm going to take, basically my plan is for each generator, I'm going to do random, I'm going to take 3 random elements of B and add them together. Well, maybe add some coefficients times them. Does that make sense? So I'm taking the ring of the first one. Sharp sign is one way to do indexing. So if I come here and I do B sharp sign 4, I get A times E. Okay. So B sharp sign 0 is just the first one on the list, A squared. And I take the ring of it. Since I didn't pass the ring in, I need to know what that is. And K is the coefficient ring of it. That's, in this case, Z mod 5. That's the Z mod 5. Okay. And now what I do is, just like we did before, I take for one from ngens, I'm listing. Okay, so I'm going to get that. And now for each polynomial, I'm taking max num terms, which I'm going to set to be 2 or 3. And I'm going to take a random element of the field, and I'm going to multiply it by a random element of B. So this is hopefully a random element of B. And that gives me a bunch of elements, and then I'm going to make it into an ideal. Okay, so let's try it and see what happens. Okay, let's take a simpler one first. Let's do I is equal to random sparse. Let's do a monomial ideal, except it'll have coefficients. So 4 of them, but each one has at least one term. Look at that, 0 is one of them. Wait, can that really be the case? That 0 is one of them? Well, I'm in Z mod 5. 1/5 of the time, the constant is going to be 0. So it's pretty it will happen quite a bit. Okay. Anyway, we don't want things in with one monomial. Actually, we do, but this is actually not going to be so interesting. If we do it again, are these all different monomials? They actually do look like it. Let's do Betty res of this one. I get a very, very different Betty table. There are 4 generators still, but there are 2 linear syzygies on it, and normally there are 6 quadratic ones that are casual, that are the trivial ones, but some of those might be in the submodule generated by these 2 here, but then we get 4 others. Are these 4 from the casual? Probably, but that would have to be checked. Hard to tell from this. And then there are 4 linear syzygies on those guys, and then 1 linear syzygy on that. In fact, if we do res of what is that guy here? I, res of I, and I do oo.dd, here are the maps. So there are my 4 monomials, and sure enough, I have 2 linear syzygies on them here, and I have 4 quadratic. They are all casual ones, but it just so happens that all the other casual ones are obtainable from these things. And then I have 4 linear, well, they're linear in these variables, but they have to be quadratic in these in order to make it homogeneous. And then those 4 all have the same degree, so there's 1 syzygy on all 4 of these, minus f times this column, minus c times this, minus b times this, plus a times that is 0. Okay. Oops. Okay. Now what I want to do is I'm going to run this code. Here, let's put this down here. Again, I don't know if I need parentheses around it, probably not. What I'm going to do is I'm going to run 1,000 times and do sparse things where I have take 3 terms each, okay, and see what I get. So I'm going to do random seed just to, so I can have, you don't need to do that when you're doing it yourself. It's nice though, because if you find some really interesting behavior one, you might never see it again. So if you don't save the ideal, you're out of luck, okay? So here, what do we get? We run that, okay? We got, if I actually look at that, 035 is the number of it, even though the semicolon meant I didn't print it. But 035 is, okay, there's a lot of things. Ooh, there's a lot of 14641s, but there's some other ones that are weird, 141 and stuff. So let's tally this. Oops, I can't tally. Yeah, I can tally that, I guess. Let's do it. And what did I get? Ooh, I found a whole bunch. Actually, it's hard to read those, but just to give you an idea, this 14641, the complete intersection one that we have, it occurred 395 times, even in this very sparse thing where we're only taking 3 terms. So it's still by far the most common thing. And look at this one, 14641, that happened once in the 1,000 times, or how many other times we ran this. Okay, it'd be nice to know how many different tables we have though, because part of the problem was to figure out, let's see if we can get all of them. I don't know if we obviously don't know if we're going to get all of them. And it might be that it's a needle in a haystack, that there are some that are so rare that you won't find it by random search. That's actually still possible. I don't know. Okay, so let's do this, go back, and I can tally that guy. I think I can, I already tallied it. So in fact, what I want to do is it's a hash table. I can do keys of it, and that'll just it will get rid of it's a key. So I don't know if you're familiar with Python, but if you are, they have these, what do they call their things? Dictionaries. What? Dicts. Yeah, right. So, and they have keys and values, right? And so if I just want the keys of it, I can do keys of 00, and I get all of these different ones. Actually, let's call these Bettys. Okay, I should have run it. I'm going to just do it here. Bettys equals 00. How many are there of those? Number of Bettys? We got 24. Let's take a look at them though, okay? So one way to look at them is there's a few ways that in textual land here, you can look at it a little nicer. I'm gonna pack the list of Bettys, 4 per row, and I'm gonna print it out sort of nicely. Oops, 4 per row doesn't fit. How about 3 per row? Okay, that does fit. So here is what we get. Look, some of them have less number of generators. That makes sense because we didn't actually guard against that. But we know that they're going to be at most 4. But we get some really weird ones. Here's a 4, 9, 8, 2, you know, like this. There's 1 extra quadratic syzygy that, 3 extra quadratic syzygies, other than the 6 causal ones, the 6 trivial ones. So that's weird. But some of these, yeah, so here we get a bunch of stuff. We might kind of, yeah, I mean, look at these things, 1, 4, 8, and then it's a whole bunch of crap. 1, 4, 6, 2. These are all pretty interesting ones. But we kind of don't want the ones with more than with only 3 generators, because we're trying to figure out the 4 generator ones. So I'm going to change the function a little bit. I think I have it down here somewhere. Thought I did. Nope, not there. Maybe this. Oh yeah, yeah. This is another version of the random sparse, okay? So this is pretty much what we had above. B, number of generators and max num turns. So we have to have this B around. And then we do R, K is equal to coefficient ring. L is for every generator, we make this thing here. Let me make this so we can see it. Okay. And we make the ideal. But this time around, what we're doing is if we take min generators of it, if it's not equal to the number of generators we want, we just redo it. We just call the same function again and return that. Otherwise, we just return I. The thing is, it won't happen that often. So, I mean, it could, there's no reason why this couldn't just keep infinitely recursing, but probability-wise, it won't. So let's run this thing. Set a random seed, and now let's do 1,000 of those. Okay, let me see what I've got going here. Okay, I'm going to do 1,000 of these things. Okay, that actually took no time. And now if I tally that list, I get, let's see, which one's 180. This one appeared 180 times on the list. Okay. This one appeared 423. That's the same one that we expected. So you know, it's still a lot of times, but there's other things. And now what are the keys? Okay, here's this. Actually, this one I have to pack 3 at a time. And I think it said that we had 15 of them, but in fact, I'm getting 16. Maybe I didn't set the random seed. So here I get 3, 6, 9, 12. 15, 18, 19 of them. So I found 19 different ones that have 4. That's a lot. You know, when I said, oh, this is the easy case and stuff like that, I had no idea there were this many. I figured there were maybe 10 or something like that. And I thought that there was a theorem of Eisenbud and Harris that classified all of these. But that's not correct. I think they classified ones that had a linear syzygy or something like that. Whereas a lot of these are, this 4 to 6 here, this is a really interesting one, actually. Look at this. If I look at the linear syzygies, what does this tell us? This tells us that the entries in the linear syzygy, okay, I have 4 quadrics. And then this one says that of this one here, that's 4 polynomials, that's the syzygy, right? You always have 4 things. They all have degree 5. So it's degree 2 entries, and you've jacked up the degree of the syzygies to 5. This does not happen for fields, right? You don't get any of this kind of behavior at all. So this is a very interesting one. And we've already got 19 of them. So let's go back and take a look. I'm going to set a random seed, and let's do 10,000 of them now. Oops, I didn't keep the other ones around. So it might let's, I should probably, let's see, we did name it. Let's call it all Bettys. So we have all of these cases, keys of OO, okay? Actually, I want to see how many I have of those. There are 21. So I had 19 before, I got 2 more after doing 10,000 of these things. Is that it? So we can actually net list pack of these keys, tally of that list of all Bettys. That's this, and then keys of that. Oops, what did I just do? Right here, keys of it, and then packing it. But again, we want to do it 3 per line because it's too large otherwise. And we look, and even here it's a little large. So we can probably, yeah, I don't know how to go partially over. But in any case, so we have here 3, you know, some of these, again, a lot of these are, they're going to be pretty much the same, except for a few extra ones. Okay, so now let's keep going. Here's another list where we're going to do 10,000 more. And we can do the same thing, keys, a tally of that, net list of it, so we can see them. And this time I get 21 different, actually, I don't know how many different ones I get. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I only get 16 here, so I must be doing something a little weird here. But at any rate, now I'm going to join my 2 sets of Betty tables. I have all these Betty tables, so I'm going to join them. Yep.
You were packing 4.
Oh, yeah, okay, good. That's good. Okay, so we have a bunch of them. It looks like we have the same number, although I'd have to actually, we could actually take a look. If I do this thing here, and I do this, and I do number of that, I do have 21, okay? So I have 21 before and 21. Are they the same ones? Well, what I can do is I can join the list of all of these things, and now I can take, again, tally of it, and keys of it, and then do it. And here I get 22. Oops, I should, let's do 3 of them so we can see it. And so it's going to be 21 and then 22. So we picked those 21, even though they each had 21, they weren't the same. So so they're 22 total, which is kind of weird. But now what the thing is, you might want to actually do a little bit more with this. You don't want to just know the Betty tables. You might want to know examples of each one as you go. So so let's try that. So what I want to do is I want to keep a hash table around that or a deck, that around that will keep a Betty table and then one example of an ideal. Once I find more, I just won't add to it anymore. So here's what I could do. Let me put this on the next line here. So I'm going to make a mutable hash table. If you do hash table, then you can't add to it. So mutable hash table, you can add new things to it. This is going to take 2 things. It's going to take a hash table. I should have said what this is. H is a mutable hash table. And I is an ideal. Okay. What it does is we calculate its Betty table. And then what I do is this is checking to see if it's a key. Sharp sign B, H sharp sign B would be the actual value of it, but a question mark is actually querying to see whether it occurred already. If it does not occur, then what it does is it prints it out, says it found a new one, and no, if it isn't there, it sets it. It sets H sharp B. That's setting that that element into the hash table, and it's leaving it as a string so you can actually get at it easier later on if you see it. And then it said it's found a new Betty table, and then that's it. It doesn't try to count how many times they happen or something like that. So let's try this. Okay, now I can do add ideal if new answers. Oops, I screwed up. Did I not define answers? Oh, yeah, I didn't define answers. Yeah, I have to do this line here. And now if I do this, random sparse is the same function we had before. And sure enough, it found a new Betty table. It had to because it was an empty mutable list. There was nothing in there. So the first one was going to be new. And then here is the ideal that it has here. So we can take a look at that. So then we can actually just textually grab this later on if we want, or we can keep it in a table. And we can peek at the hash table, and then here's the key, and then there's the ideal. Okay, so now what I want to do is I'm going to make a new one, and I'm going to do 1,000 things here. Okay, and it found a new one a bunch of times. How many times? The number of keys of that hash table are 18. So it found 18 after that 1,000 tries. Let's do 10,000 more of them. Oops, let's make it so we can see this though. And this one, we should be able to see it too. Okay, so here I'm going to do 10,000 more of them. And it found a couple more. And it's done. How many does it have now? It has 20 total. This is a little easier. You can keep going and you can just set it running and then you can get it and you can look at it. So if it ever dies, you have the ones in hand. So for instance, now I can do another 10,000. It found another one. And now I'm at 21. That's how many I had last. No, I had 22 before. So we're not quite there yet. So if I do another one, 10,000, I picked up this one. This is a very interesting one. It's 1, 14, 13, and then a whole bunch of linear matrices. And how many are there here? There's 22. And I do it again. 22. I do 50,000 of them. Yeah, that's going to take a little bit longer. Okay, that's a lot longer. And how many do I have? 22. Conjecture, there's only 22. However, we did this for a specific number of variables. So I want to kind of increase it up here and go up to, actually, we have to really define our B though again. So we need to do flatten entries of basis of 2 in R. But we're now going to go up to this number of things. And now I'm going to take all of those. I have a lot more. And now let's make sure that this line here is what we think it is. Now it's going to take random binomials where there's only 2. Okay. And we'll see if we get a new one. Nope. Okay. It takes a while. But there is a third one. There's one down here that gets found. And after that, I've searched. Just last day or two, I searched over, maybe 10 or 20 million examples, and found no others. So now, after that many, is the 23 good? I don't know. This is not necessarily the only way to choose quadrics of this, and it's not a random search because I'm choosing very specific ones. So, I mean, this is already there's a theorem in here that no one has actually, I don't know what it is, but there are a few things that you can actually say though. These Betty tables have some interesting properties. So if I do pack net list of pack of keys, keys of our answers, right? I think that's what we called it, by 3 at a time. Okay. And here we have all these. I'm going to make it just a little bit smaller so that we can see them all. Or maybe that means now you can't see any of them. So there's a few pieces of information you get out of this. One of them is how far back it goes. That's the projective dimension that we were talking about earlier. Okay. And that is 5 here. Okay. For S mod I. And if you look through all of these, that's the largest one that appears. Here's another one that goes to 5. Oh, wait, here's a 6. projected dimension 6. So far, I haven't found any larger than that, which isn't that surprising since I was doing it in 6 variables, so it wouldn't go higher than that. But if you do under 8 variables, you might see it. Okay, so there's all that. And and then that's one thing. So the number of columns of this Betty table is the projective dimension. It's unknown what the maximum dimension of projective dimension of this kind of ideal is. I think it's conjectured to be 6, but I don't think it's actually known. Might be known. Jason McCullough might have an argument, or they're actually him and some of his co-authors might have an argument for that case. What's not actually known is what is the maximum number of rows. So how far in degrees down do you have to go? And that turns out to be another really good invariant called the regularity of an ideal or of a module. Is that this number 4 is the regularity of S mod I for this case. And for a complete intersection, it's 4. And actually here it's always less than or equal to 4. But there are some weird ones. Here's one where it has degree 5 syzygies, but it's still regularity 4. And that's the highest one that we see here. So conjecture, that's it. Can one prove it? I don't know. So it's kind of tricky. But there are other things you could compute here. So we have the projected dimension. I didn't actually say what the codimensions of these things are and what the X modules are. I haven't even looked. So there might be some very interesting results that one could find there as well. So, but ideals of quadrics turn out to be really very interesting. They contain all varieties eventually somehow. You can, if you re-embed a variety in projective space in high enough dimension, it becomes generated by quadratic polynomials always. Or some of the very worst complexity ideals are generated by quadratic binomials. Like the highest regularity ones that are known are like that. So very weird. I mean, there's a lot of variables, but nonetheless, that's what you have. Okay, I think, so I just wanted to sort of show you this. I think what I want to do now is have you play around with some of the stuff here. Are there any questions on this kind of playing around? I didn't really mean to go that long at it.
So you have a field of 5 elements.
Yes.
You have 20 coefficients.
Yeah.
That's a huge combinatorial
It
space.
sure is a huge combinatorial space.
Sampling.
I've only sampled a little bit. So what have I missed? I am finding the generic ones in that space. So the question is, how can I find all of them? I don't know, actually. I can do it long enough but if I'm looking in a different way, I might find there might be a different way of zeroing in on interesting ones that are not these. And I have no idea how many more there are. And so anyway, this is an interesting little, computational problem that you can play around with. Even for 4 quadrics. You're not even going to 5 quadrics, can do that. Okay, here's what I suggest now. I suggest, especially if you haven't done this before, I would do problem 2 first. But problems 2 and 3 are really good. 3 is kind of goes along the line of proving that Serre thing in P2 and thinking about what that means in terms of in terms of each monomial and stuff like that. That's a good theoretical one. But the problem 2 you can do by hand also, because for at least except for the third one, but there's 3 problems here, A, B, and C in problem 2. I would start with the cubic surface in P3. That's the one that has 27 lines on it. All cubics do. The quartic surface, which is very similar. This is a Fermat quartic, but any quartic, those are as long as it's a non-singular variety, which we haven't really defined yet, is called a K3 surface, which is a very interesting surface kind of surface. And either one of those, the cohomology is kind of interesting to see. So so I would recommend that would be a good problem to play around with. Even the Hilbert polynomial, the dimension degree, you can do it all by hand, but I would also check it with Macaulay too, if you haven't done that kind of thing before. If you have done it, problem 3 might be good. If you've really done all that, then problem 4 I wouldn't do yet because we haven't done local duality yet, which we were going to do. We might It's 12:10 now. I suggest that we actually spend we spend a half hour doing this and then we get together and discuss these things at the end of it for the last 15 or 20 minutes. Sound good? Okay. Go for it. And if anyone wants me to email them this thing, what I really should do is just get an email list. I'll try to get this put on the website, actually, this sheet. I'll try to do that. I'll ask Lynn later today if we can do that. And if anyone needs any suggestions or hints or or you want something else, I'm here. By the way, for 5 quadrics, I think I got around 100 tables so far. I don't know how many there are there either. Yes.
Was there a point in our code where we had 2 lists? One was 21 distinct Petty tables and the other was 21 distinct Petty tables. And then we concatenated those lists and counted them.
Yeah, how did we
got
get 22? Yeah, I was actually wondering about that. That doesn't make sense, does it? Maybe I had the number wrong. Maybe one of them was 21 and actually that's an interesting question because it had to be it couldn't be. I was actually thinking of that. And I'm going, wait a second, but then I got onto something else. So I'll have to go back and take a look at that. Usually, maybe it's down here. I can still go back and look. What was that? Those were called something. That was when we did a join, right? Join right here. And so we have 21 of them.
Yeah.
Oh, I didn't see how many we had for the first one. Oh, maybe it looks like we had 21 there as well. Okay. So
We just have like.
so if I have 21 and I have 21 and they're different, that means that there has to be one here that's not in there. There has to be one here that's not in there. Oh, I see. No, that's 22. That could be. There's 20 in common. Yeah, there's 20. Yeah, that's right. That's right. Yeah, obvious. Yeah, right. 20 and 1, 20 and 1. Oh, yeah.
I was assuming
Thanks.
that one would have all 21 in common.
Right. I mean, it's kind of interesting. You see 2 lists of 21 after a search like this. You say, oh yeah, they're going to be the same, but they're not. So that's kind of interesting. But you're right that it's 20 and plus 1, not 21 plus. It's unclear how many variables you need. I mean, we found ones that went up through 6, but could there be one of higher? I think that maybe. And certainly, I don't know what the maximum regularity is. Just make would be nice if there was one higher, but it's gonna, yeah, those things get harder and harder to find. So it's kind of interesting. What's interesting is if you look at, well, anyway, I'll let you do the other things. We can, if anyone's interested in talking about this stuff, there's I'm more than happy. I find this actually analyzing these things, even though it's a special case kind of thing, is kind of interesting. Like for instance, here's one possibility. Suppose that we haven't really talked about minimal primes yet, but suppose that minimal prime is just a set of variables, like 3. It's codimension 3, say that's the standard one. X1, X2, and X3 are the 3 variables that say that form that. That means all the other polynomials are something times, x1 plus something times x2 plus something times x3. So, and there's 12 possible things. So you could make the ideal that has 12 variables plus the 3. If that's 15 variables, anything of that sort would have to be a specialization of that. So that really gives you a global way of trying to figure out all the possible things. And that's where all the complication is, are the ones that are like that. Almost all the other ones are kind of nice.
But the code on the website, would it be as like an M2 file or as like a TXT?
That's a good question. It will probably, I'll have to put it as probably that's why it didn't go up before, is a .txt, but you don't have to have it as in Macaulay 2 as in using it as a .m2, but it's a lot easier if you do. And do you want me to I can put up both the result and the actual code that we started with. We didn't do all of that code, and we played around with it. So but I'll put both of those up, and I'll try to do that. Yes.
Just create a public info.
It's good. That's a good idea. Actually, that's a good idea. And what I would like to do is actually make a Jupyter notebook that does this kind of stuff. But yes.
You prepare the notebook ahead of time, type
Yeah, I know, I understand. That's a good idea. But it is a good idea but it's also, it's even with the Emacs, if I hit F11, it's hard to follow what's actually there. You have to kind of go back and do it.
Are you aware of capability of Jupyter notebooks to create a presentation, like slideshow?
I sort of am aware of that.
Just mark it.
Yeah.
headings, And then there's map, generate the slideshow. It just uses each heading as a start of the slide. The slide can go beyond like the length of the screen.
But you can scroll it up. Okay.
Just
Yeah, actually, I have to play with that. I haven't done that. And that would be good.
Prepared lecture. Live.
Yeah, actually, there it would be not so awful to have even this stuff up on that. The trouble is that the tech that you can use in Jupyter Notebooks isn't so good for some of the stuff. You can't use ticks, which is maybe you can. If you can, that would be awesome. I'd be.
No, I'm not. But yeah, I think there's probably like
There's probably something that allows you to do that. Yeah, I looked at it. No, it doesn't. In fact, they say they won't do it because it's too involved of a language, the whole ticks thing, which I totally get. I mean,
you don't want to recreate.
question?
No, sorry.
Okay. Do you want me to? I can shut up too, so that guys can think.
We're stuck on 2x. We don't know what the degree of x is. How to compute.
Oh, we just don't know what degree is.
Okay. So we had defined that at one day. And that was if you look at the Hilbert series, or if you look at the Hilbert polynomial, you can try doing it in Macaulay 2 too. Actually, for Hilbert polynomial in Macaulay 2, it's a little annoying because you might want to do the following. You might want to do Hilbert polynomial. I think you can do I, and it will mean the co-kernel, the S mod I. But you can also do S to the 1 mod I. And then you do projective gets false. So the default is true, but that takes a little bit of, and it's a good format, but it takes a little bit this should really be the default. So this gives it to you as an honest to God polynomial in some weird variable like I or something like that. By the way, in Macaulay 2, you can also type degree of I, and it'll give it to you too.
We did that.
Yeah. But if you want to know how to compute it yourself, you typically you're doing degree 6. Oh, so you're doing the last one?
No, big surface. This is just a conceptual.
Oh, yeah. So the degree, yeah, that's a good point. So the degree there you can compute directly by using the free resolution of S mod I, where I is just generated by that one polynomial. So that's actually good to make sure you know what the free resolution of that is as well.
Is the degree just a degree of polynomial, or I forget, like, you also have
No.
variety.
So yeah, let me can I erase this stuff, or do we need it for anything at the moment? I think it's okay to erase this. Oops, I got rid of that. So wait, sorry, what was the question? Oh yeah. So let's suppose that P of T is the P of let's call it Z. This is the Hilbert polynomial. Okay. So what does it look like? It looks like Z to the D for some number D, and then a coefficient out front. And that coefficient is going to look like E over D factorial. And then this is going to be lower powers of Z. Okay. And D is the dimension of the, as a projective variety of this thing. This is all homogeneous ideal, right? So D is equal to the dimension of the zero set of I. This is of S mod I, contained in projective space. Okay. And this is just the zero set. And then E is equal to the degree of that set, which geometrically is defined as a different way. So if I have a variety inside a projective space, I can intersect it with a linear space, and it goes down one dimension. I intersect it with another, at least generically it goes down. But I do it with random hyperplanes. And I do it until it keeps dropping down in dimension until I get down to points. And if I've done it randomly, it will intersect in that number of points. So for instance, if I take a cubic plane curve, and I take a line, how many times does it intersect it? It can intersect 3 times. Obviously, if I take the cubic like this, and I take this line here, it will intersect 3 times. If I take this one, no, 3 times over the complex numbers. Okay, so but there are places where it'll only do once, like if at inflection point, it'll hit it with multiplicity 3. So as long as your line misses all those things, it will count exactly 3. That's Bezout's theorem. It's a really good theorem, which you can actually prove using all this stuff too, but sort of. Anyway, these are 2 pieces. These are somehow the first piece of information about a variety that you would like to know. The other piece that you would really like to know is what's the constant term of this thing. That turns out to be essentially the arithmetic genus, whatever that means, but it's another number.
Whatever.
Well, so for instance, for an elliptic curve, so the genus is supposed to be a torus, right? So it's supposed to have genus 1 as a oriented surface. And in fact, you could get that G equals 1 from it's not exactly the constant, it's 1 minus the genus is the constant term. So but you get this, it's pretty good information that you get right off the bat for this. But then there's other information you might like to know, like, is my variety rational, or does it have, lines on it, or, all this other stuff. And so cohomology helps with some of that. And that's what we'll be using it for. I didn't actually explain to you how to compute these cohomologies using Macaulay 2. Would you like me to give you a little So suppose I have an ideal I that's homogeneous. What I can do is I can do x equals variety of I. By the way, the varieties, it's being moved into a package. Right now, you can just type this and it's all fine. But eventually, you might have to load the package. But anyway, right now, this is still the case. So you do x is equal to this. And now, if I just type HH, so all of the there are no single letter things in Macaulay 2 that would be annoying to use up all the single letter things. But HH is how you do cohomology. So you can do this up arrow I, and I believe you just type O sub X will give it me that cohomology. And I can also put a parenthesis here and put like 3, if I wanted the cohomology of that one or something like that. Actually, is that working? Here, let me actually do it and see. Maybe I've forgotten something.
Can I do something just directly with the ideal instead of passing through variety command?
You certainly can, but if you want the actual sheaf cohomology done, this does all the stuff for you, whereas you can do it by the stuff we're actually doing today, and I probably finishing next time is to show how to compute the cohomology. So actually, do I have an ideal I here? That's not a very good ideal. How about if I do S is equal to, I always like finite fields. Let's do, no, not at all. Okay. Can you see it? So let's do a specific example. Should we do one of the ones here? We could do the 3 by 3 minors of this 4 by 3 matrix, and then you'll have it here to play around with. How many variables is it? Oh yeah, those are capital O's. So do you not need this, or should I do it anyway? I'll do it anyway, so you have it for later. So here's my ring S, and I'm going to take a random set of polynomials. And actually, I'm going to take a random matrix. Okay, so
So it's because that's not the last output, that's capital O.
Yeah,
as in the
that's
sheaf.
what I thought. And then I would go to this last one. Yeah, eventually.
sorry, what? So you can give it, this is a map from this space here to this space. So so this is really, it's like, if you think about it's homogeneous of degree 0. So it's going to be a 3 by 4 matrix, so there's 4 things here, and they're all going to have degree 1. You don't have to do it that way. You could do random 1 comma S and just make a matrix out of it. That would be that's probably this is kind of a little slick. You don't need to do it this way. And then I took the 3 by 3 minors of this, and then this is what I get. But then we wanted to do HH up arrow something. How about 1 of OO underscore, oops, I didn't say what X is. We got to say X is equal to variety of I. Okay, it's a projective variety. If I do OO underscore X, what do I get? It's a sheaf of rings. OO underscore X twisted by, say, 3 is a coherent sheaf on X free of rank 1. Okay, fine, whatever that means. And then we can do HH up arrow 0 of this. And it's one copy of the field. So if I do rank of that, I can't do dim of it. Dim of it will give the dimension of it as a ring. So that's not what you want. So the rank of it is 1, and that's really the kind of information you probably want from this at the moment. It turns out, by the way, one thing that you can tell, if you have a projective variety whose H0 is one-dimensional, then it's a connected space. It might have multiple components. It might have x equals 0, y equals 0 meeting at a point, but it won't have two skew lines, for instance. Each one of those would have to give you at least one copy of something. So actually, how about rank 1 of that? And we can actually, one thing that you can do is if you want that whole module, you could do something like this. Oh, actually, this is 0, but maybe they're not always 0. Let's take a look. If I look at the truncation in degrees greater than or equal to 0, no, it's the 0 module. So that's not so good. And if I instead take H0 of that, what do I get? I get some big mess that I can't actually see what it is. Actually, what is it? What kind of object? It's a module. I see. So it is returning a module. If I let R equal the ring of that module, 097, and now I look at 097 again, it's R to the 1. So it's a sort of very simple module. They don't have to be that simple. But this is an interesting surface. Later on, if we get into it, I mean, what kind of surface is it? You know, like, is it a rational surface? Is it a K3 surface? There's all sorts of these different kinds of things that one could ask. We probably won't do that in this class, but it's an interesting computational story. Okay. Oh, right here. So here I made a polynomial ring in 5 variables. I could have used Q, but the random numbers over Q are chosen to be very small, so it's kind of not so good. And so I take this, and here's a 3x4 matrix of linear forms, and I just take the 3x3 minors.
Well, for me, that's the work around the thing, so it's like, okay, let's see what.
For which one? This line here?
Yes, that's.
Yeah, this is a weird one. I can show you a different way of getting it as well. This is probably not the way I would recommend people to. I would rather probably just doing random of s comma 1 comma s will give you a linear form, and then you make a loop and you do it enough number of times, and then you make a double loop to get 3x4 of them or something like that. It's probably a good practice in using basic Macaulay to get what you want. And then this is kind of annoying. This is a big long thing here. And then after that, the Hilbert polynomial. So this is the 3x3 minors of a 3x4 matrix. You should take a look at the free resolution of it and see what it looks like. And but we can get the dimension of this as a variety in projective 4 space, right? We're in 5 variables, so in projective 4 space. And if you do dim of it, you will get the affine dimension. If you do codimension, that can tell you what it is also, codim of I. But you can also get it from the Hilbert polynomial by just looking at that. So what does that tell you? What the polynomial being the polynomial where it is 3i squared plus I plus 1. There would be 3z squared plus z plus 1.
So the dimension is 2.
Yep. So it's a surface in projective force space. And its degree,
It's going to be
not quite. There's that d factorial down there. So it's degree, so it's a constant 3 there, but if I put it divided by 2 factorial, it's going to be 6. 6 divided by 2 factorial will be 3. So you basically have to multiply that number by the dimension factorial to get the degree.
Mike, can I ask a quick question?
Yep.
So just this is in general about the fact that you're using a finite field. Like, do you have to try your code with like, I don't know, 2, 3 different finite fields to be able to make projections or guess? I mean, whether you're, computing these sheaf cohomology groups or you're computing these Betty tables. Because
So
I was running my code over QQ and it wouldn't even generate like 100 random Betty tables.
it would not do 100 different ones?
No, because I don't know. I let it run for 5 minutes. It didn't get anywhere. For the quadrics. So I had to change the field to like Zmod 100. I had to change to a finite.
Actually, it should work fine over Q. You just won't find anything interesting so easily.
I see.
But you should be able to run it, and you'll probably see that you get the complete intersection almost all the time. Unless you do the random thing that we were just talking about, where you restrict the number of monomials in a polynomial, would be 2 or 3 or something like that. Then maybe you would get interesting things. But in general, the way it works is if your thing is defined over the integers, then you have a free resolution over the rationals, and you also have a free resolution over every mod prime every prime p that you can mod out by. And the thing is that there's a finite number of primes p where you will get a different Betty table than the one over q, and most of the time over p you will get the same one as over q. So I have never yet seen an example in the wild of something mod 32,003, for instance, that isn't the 1 over q. Every now and then people think they have one, but it turns out then they forgot to add in some equation. Obviously you can make it that way. If I have an integer over an ideal over the integers that is 32,003 times x, then that's going to be a big difference mod 32,003. So in that, but here's another thing you could do. You could do it mod several primes and then lift the answers also by using Chinese remainder theorem. But you have a problem in doing that because you have to make sure that the format of your answer is sufficiently normal form that you can actually do such a thing. And with resolution, that's a little harder to do. It can be done, but it's not so easy. So another 5 minutes or so that we can discuss those problems.
Add a package for using the Euler for finding the.
I don't think so. It should be lowercase EULER, and then you give it a module, or you can give it a sheaf. So what do you it's not working?
No.
Let me see. Oh, I see. Put an up arrow 1 on it. That's good. That's, I'm sure, is fixed. Actually, I don't know if it's fixed. I'll have to check.
Yep. 1.
Maybe upper one not here, but there. Okay.
Yeah. So in other words, it's only defined for a not a sheaf of rings, which is O underscore X's, but upper O1 makes it into a sheaf of modules. That's should be, yeah, that might be fixed in the people, and some of the people here, in fact, like Marud has been working on it, has been redoing the varieties functionality to be able to handle maps between sheaves and stuff. Just like we haven't really talked about what a map between sheaves looks like, except what it really is you truncate the modules and just have a map of sheaves. I have a map of modules, and so it's, yeah. So there's a bunch of stuff that has to be done to make that all nice functorial, and they've been working on it. But that kind of thing where it doesn't work for a sheaf of rings rather than coherent sheaf is kind of annoying. Hopefully that's fixed too. I'll check on that. Did I say what the Euler, did I talk about the Euler characteristic? I did. Do you know what the Euler characteristic is even of a sheaf? I thought I wrote this, but I never got to it in the thing. You know it, but so if I take a sheaf, F, or here, let's do it over here. This is actually kind of cool that, so if I have a sheaf F, which is M tilde, this is on Pn, okay, or on some, you know, it will be on any variety in there. But and now if I take the sum of -1 to the I times the dimension over the base field K of H to the I of M tilde, okay, or of F, right? So if I do this, this is called the Euler characteristic of F or of M tilde. And this is I equals 0. I didn't say where it has to go up to, but in fact, it's up to the dimension, say n here. Okay, so this is the Euler characteristic. Now, this seems to mean that you have to calculate all of these things. But suppose I take, let's suppose that P of M of Z is equal to the Hilbert polynomial of M. Then the statement, which you can prove, is that P sub M of 0, this is the constant term of this polynomial, is in fact equal to the Euler characteristic of M tilde. This is extremely useful fact. This is pretty easy to compute. One Grudner basis computation gives you the alternating sum of these cohomologies. Some of these can be very hard to compute, so you can use this to save yourself lots of effort, or being able to compute things. Maybe I'll let you think about how to prove that this is the case. But you have to use the long exact sequence and maybe some free resolution stuff. Unfortunately, the alternating sum is not always what you want because things cancel and you can't, you want it without cancellation somehow, but that's oftentimes harder to come by. Okay, so we have 15 minutes left. So should we talk about this? Did people do any of the problems? Which ones should we consider?
I was doing that, but that's problem 3.
It's problem 2. Oh, which one? This one over here? I didn't do that. I sort of explained how you might do it, but how do you actually do this from and then go to? Did other people work on that one or not yet? Were you doing some of the other ones? Right, okay. I think we should probably go through question 2 first. I think that's actually a pretty good one. By the way, you should think about how you would calculate how many lines there are on that surface and stuff like that. But at any rate, so problem 2 is it says consider one of the following 3 varieties, either the cubic surface in P3, which is this is the Fermat cubic, x cubed plus y cubed plus z cubed plus w cubed equals 0, or up the degrees by 1. Actually, any degree it would be interesting, but that one's interesting. The first one's called the cubic surface, which is an interesting thing. It's a rational surface and so on. It's actually projective plane blown up in 6 points and things like that. So there's kind of a lot of nice geometry floating around that. But the Fermat quartic is also interesting. It's what's called the K3 surface, which is a very interesting kind of thing. We won't see too much of that here yet because we haven't done enough to do it. But once we see how to compute the sheaf cohomology of the canonical module, all of a sudden, actually we know how to compute the sheaf cohomology. Well, we sort of know. We don't really know how to do any of it yet. We know how to do it for projective space. That was the Serre thing, but we haven't actually talked about. Well, we know how to do it by this kind of thing, but in practice we're not quite sure yet. Anyway, let's talk about. Let's do it by computer, I guess. So this is going to be problem 2. Should we do A or B, C, or C? Which one do you like the best? Or did you try? A? Okay, so I am going to do S is equal to, should we do it over the rationals this time for a change? And what do you want to call the variables? I call them X, Y, Z, W. Okay, so there's our polynomial ring. And now we want our ideal is going to be just the ideal given by one, by what? Actually, this thing is kind of annoying, this little note here. I don't know how to, I can do this, I guess. Okay, I equals ideal of, what is it, x cubed plus y cubed plus z cubed plus w cubed, right? So that's the ideal. And what did it ask us to do for that? Find the Hilbert polynomial and the dimension and the degree. Okay, so I would do, first of all, what you can do in Macaulay 2 is you can do codimension of I, which is 1. Okay. And you can also do degree of I. What should that be? Well, it's a cubic polynomial. It should be 3, but that's, that needs some thought. Okay, so it's 3. And now let's do the Hilbert polynomial. If I just do Hilbert polynomial, what do I get? I get some like wacko thing. But what this is really is it's the Hilbert polynomial 3 copies of a P2 minus 3 the Hilbert polynomial 3 copies of a P1 projective line or plus a point. Those numbers are actually kind of useful. There are various multiplicities that occur combinatorially nicely and stuff like that. But if you don't want it that way, you can do it this way. Until you get good at reading that, it's you do projective. That's the sort of projective spaces, right? Projective gets false, and it gives it to you as a polynomial in this. Okay, so what does this tell us? This 2 is the degree of this polynomial, which tells us that the dimension of the 0 set of this ideal I is 1. No, it's 2. So this is a surface in projective 3 space. And its degree is 3 because here's I squared over 2 factorial and then 3 times it. So it has degree 3. Some of those things are pretty easy to prove using exact sequences of sheaves or of these modules. Okay, that's that one. The dimension and degree we just got directly from this. So that's the answer, right? So the dimension equals 2 and the degree equals 3 from this polynomial. Okay, good. What's the next question? Find the dimension of the cohomology vector spaces of OX using exact sequences. Okay, this is the main part of this problem. So how do you do it? Yeah, so let's actually resolve it. Here, I'll do it. We don't need this any, well, let's do it over here. So what's a free resolution of S mod I? So I is one generated, right? Let's call it F. So it's S, and then here's the generator F, and that has degree 3, right? So I have a -3 here. What's the kernel of this map? Nothing. Or well, it is something. It's 0, but nothing other than 0. Okay, so this is the free resolution of this. Okay, now what? One option you can do is you can take tilde of this whole thing. And now let's suppose that X is the 0 set of I contained in projective 3 space, right? So this is going to be OX. This is going to be O of P3. And this is going to be O of P3 twisted by -3. And then there is some indication on what the map is here. It's the map multiplied by L. Okay. So now let's do maybe the long exact sequence. Actually, if you don't mind, since we wrote the long exact sequence the other way, let's flip this around. So this is another way of doing this would be just to do O of X. And maybe, in fact, a lot of you will prefer this. So is this sequence here, right? So now let's apply H's to all of this. So I get H0 of this. So I get H0 of OP3 of -3. I might actually be interested in all degree shifts of this thing, but let's just do it for this one, which is I think what I asked for basically. So this is going to be of -3 here, mapping to H0 of O of P3 with nothing. Oops, I didn't give myself much room here. H0 of O of X. Here, let's do this. Goes to H1 of OP3 -3, etc. H1 of this to H1 of this, etc. How far do we have to go? We have to go to H2, and then we have to go to H3. Except H3 of O of X, which is down here, is 0, because X is dimension 2, and this is higher than that. Okay. So we have all these things. This is an H2 of O of X. And this is H2 of O of P3. And this is H2 of O of P3 -3. And then here is H3 of O of P3 -3. H3 of O of P3. And that goes to 0. And actually, this is going to H4, which is 0. So if this is not 0, that would be interesting. Anyway, okay, so what are all these things? So this is an exact sequence. Some of these things are 0, though. Which ones are 0? We'll cross out the 0 ones in orange. Yes. Yeah, all the ones that are on P3 here, that was the Serre result, that all the intermediate ones, not 0 and not n, which n here is 3, all the inner ones, this is 0, this is 0, this is 0, this is 0, right off the bat. That's actually pretty good. That tells us that this is equal to 0, because it's sandwiched between two zeros. This one we don't know, it's the kernel of this thing here. And this one we don't know yet either. We have to get it. So what else do we know here? We do know a lot more. The ones on P3, Serre gives us all of them. Okay, so yep,
H naught of P3 divided by -3 is also 0?
that's right. Any negative value here is 0. Any greater or equal to 0 value will be the number of monomials in that degree. So this one is 0 also. And this one? This is dimension 1. H0 of O of P3 is S, the polynomial ring, in degree 0, equals the dimension of S in degree 0. Okay. Therefore, this is dimension 1. Okay. So that's good. So dimension 1 for H0 it's a very special thing. It means that it's connected. And actually, to tell you the truth, this is actually irreducible and smooth and everything. So it's certainly 1, and so is X. So so that is the case. So this is 1, this is 0. What about H2 of O of X? That's the only one that's left, actually. So what do we get for it? Well, this one here, aha, if this were a -4, we would have a different story. Because H3 of O of P3 of -n-1, that's the first non-zero one, and then the more negative it gets, the more it grows. But at 3, it's still 0. Okay, so this x here is going to be 0 for this one. So and x has dimensions 1, 0, 0 here, like this. That almost tells you it's a projective, that it's something nice, like it's a rational variety or something like that. But it doesn't always, because there are things that have these values 1, 0, and 0 that can be more complicated. So one has to do other kind of things to check on it. By the way, what's H3 of OP of 3? It's also 0. Even if we didn't know that, if this is 0 and this 0, this has to be 0 in the middle. So all this stuff is the case. Now, what happens if we go to the other example? If we go to if we go to the quartic with a -4 here, what changes in this whole game? This becomes a -4 here, right? So the only thing that changes are these -3s become -4s. But now this becomes a one-dimensional vector space, which means that H2 of O of X is going to be one-dimensional. So and once you get into the game, that's a huge difference in what kind of variety it is. So but otherwise everything else is the same. These are all 0 here because they're intermediate cohomology. This is 0 because of the negative value. This is 1. So everything is the same here through here, except for here to here. This is 0 and 0. So the only thing that differs is whether this is a 1 or not. And actually, if it were of degree 5, it would even be higher dimensional than 1, and then so that would be even larger. But so it's pretty reasonable setup. By the way, K3 surface is the surface version of a Calabi-Yau variety, and that's exactly where essentially this kind of thing happens. But okay, we didn't quite do the whole problem though. What did I miss? Oh yeah, I think we did the cohomologies earlier. And computing the Hilbert polynomial and the Euler characteristic of these, what are they? Did anyone do both of those? You can compute the Hilbert polynomial absolutely directly from this, right? Because it's additive. The Hilbert polynomial this is the Hilbert polynomial this minus this. And that's what you get. You get the one that we had over there. So that's the Hilbert polynomial. And the constant term is 1. Now, what about the alternating sum of cohomologies that for the Euler characteristic? It's 1 minus 0 plus 0, so it's 1. So so if we already knew some of these things, if we knew 2 of them, we get the third one sort of for free. If you consider that the knowledge of this is something easy. Yep.
How are the Hilbert polynomials from A and D different?
They're not.
Okay.
No, sorry, it's exactly the same thing. That was a bad way to say it. What I was trying to get here is to compare the two. Actually, they're exactly the same. The Hilbert polynomial of X is the Hilbert polynomial of S mod I. That was really a bad phrasing. Anyway, I think that's it for the moment. Okay, so no class next week.